The Earth is bombarded with cosmic rays all the time. We have been able to monitor the energy of these cosmic ray particles for many years. In theory, there should be a maximum limit to the amount of energy these particles possess, and yet we keep discovering more and more particles that seem to break the universe's energy limit. Let's dive in and find out more. According to mainstream science, there is a hard physical limit on the maximum possible speed in our universe. This is the speed of light. Photons are considered to be massless particles, so can achieve this maximum velocity. If, however, you are a particle with mass, then it is never actually possible to achieve this speed. Instead, you can only approach it. No matter how much energy you put into that particle, it will always be slower than the speed of light. This all assumes that the particles are being accelerated in an empty vacuum, and space is simply not like this. There are obviously particles of mass, but also plenty of stray photons spread across the universe. At normal speeds, these don't really play much of a role in slowing these particles down. But as the speed starts to approach the speed of light, they can exert a significant frictional effect, forcing the fast-moving particles to slow down below a specific energy limit. The main retardation should actually come from photons left over from the Big Bang. According to the Big Bang theory, the early universe was flooded with photons, far more than we have today. More than 1 billion for every proton and neutron in the universe. Today, they believe these photons are still around but exist as the cosmic background radiation. Now, in our local neighborhood, these cosmic background photons are dwarfed by those produced by the Sun, but in intergalactic space, these become a significant factor. This means that cosmic rays should have a maximum energy limit as they travel through space. They are decelerated by the photons until they are below this limit. The problem is that for the last 30 years we've been detecting particles that exceed this limit, and this means that there must be something fundamentally wrong with our understanding of the universe and particle physics. At the moment, the Large Hadron Collider is only capable of accelerating particles to about 1/1,000,000th of the energies we see from these cosmic particles. At these much lower speeds, the interaction with photons plays no role at all in slowing the particles down. They believe that at much higher energies, the proton is able to interact with a photon in a different way. In quantum mechanics, photons can also be thought of as an electron and a positron pair. If the proton has about 1 million electron volts of energy, then it has double the rest mass of an electron at around 500,000 electron volts. It is thought that if you have enough energy to create a particle, you are also able to interact with them. This interaction should cause a loss of energy. These interactions should be rare, but if the particle travels for long enough across a vast distance of our universe, it will start to have a significant effect on its speed and energy. If the energy of the proton is even higher, then the energy can actually create pions, which would drain the energy even faster, each time by 20%. After traveling for just 100 to 200 million years through the intergalactic medium, all the protons should fall below the limiting energy, and yet they appear not to. The most extreme example of ultra-high energy cosmic rays occurred 30 years ago. The Fly-Eye camera in Utah recorded a cosmic particle with 3.2 times 10 to the power of 20 electron volts of energy, and was dubbed the "Oh my God" particle. Since then, we have continued to register these high-energy particles, which, according to the current model, simply should not exist. So how can this be explained in the current model? The first option would be that the high-energy particles are not produced in the far-flung universe, but are much more local, meaning that they have not had time to drop below the limit. The problem here is what would create these high-energy particles. The second possibility is that the particles are not just protons, but are composed of a heavier particle that would have a higher energy limit. If we examine iron, this would have 56 protons and neutrons, and therefore its energy limit can exceed 10 to the 21 electron volts. Now let's just take a little step back here, as there are several aspects that need to be discussed. I have talked many times about the many issues with the Big Bang, and to me this is another thorn in its side. If there was no cosmic background radiation, then there would not be this deceleration of the cosmic ray particles, and therefore no limit on the maximum energy. What we see as CMBR is more likely caused by something much more local in our galaxy, or a serious mistake in their equipment and analysis of their data, as Pierre Robitaille has pointed out. It is far more likely that the source of these high-energy particles is indeed more local. Halt and Arp had already shown that the majority of cosmic rays seem to originate from the Virgo cluster, which, as we have seen in the Halt and Arp evidence series, has many active galaxies and many quasars associated with them. Hannes Alfvén viewed that cosmic rays may originate from the relativistic double layers in interstellar space, accelerating ions up to cosmic ray energies. A double layer is a plasma formation by which a plasma protects itself from the environment. It is analogous to a cell wall by which the plasma, in the biological sense, protects itself from the environment. If an electric discharge is produced between a cathode and an anode, there is a double layer at the cathode and another near the anode, protecting the plasma from this electrode. Most double layers carry electric currents. A double layer must be treated as part of a circuit which delivers current. As neither the double layer nor circuit can be derived from magnetofluid models of a plasma, such models are useless for treating energy transfer by means of double layers. They must be replaced by particle models and circuit theory. Hannes Alfvén felt that double layers in space should be classified as a new type of celestial object. You will not find these mentioned in any textbooks. You will also not find any textbooks discussing the current flow that must flow in these plasmas in order to create the magnetic fields that we detect. Now, this is actually something that I'm producing a video on, which should hopefully come out on Monday, focusing on double layers and in particular Hannes Alfvén's papers on the double layers. Now, we would expect to find these double layers as part of the galactic circuit, and when Hannes Alfvén examined radio galaxies, he saw that the radio emissions were not coming from the center of the galaxy, but instead far out along the lobes, and this is exactly where you would expect to find a galaxy's double layer. It should therefore be of no surprise that we find these cosmic rays coming from the direction of some of the most active galaxies in our neighborhood. Connected to this, astronomers have also recently detected the highest energy gamma ray ever. Using China's Long High Altitude Air Shower Observatory, they were able to detect 530 photons with energies above 1 tera electron volts, with the highest being 1.4 peta electron volts. Again, Hannes Alfvén felt that both gamma rays and X-ray bursts could be explained by the explosion of these double layers. These findings cast doubt on the currently accepted mechanism for how these particles might be generated, and once more points to the importance of including the flow of current in plasmas in order to properly model and understand the behavior of our universe. As always, be brave, be curious, the truth is waiting for us. Until next time.